Okay, so in this first part of section 2.2, we're going to look at complex functions as mappings. In a particular example, we have this function over on the right here, which is w is iz. So our function of z is the multiply by I function. And in complex function land, it's not as easy as with real functions from R to R, because we can't really graph it, because the graph of a function of a complex variable lives in 2 copies of C, just like a graph of a function of a real variable lives in 2 copies of R. 2 copies of C is R4, so that's a 4-dimensional thing. So we can't graph these functions. But we can see how they take shapes or regions to other regions. And so in this example, we're going to look at the image of a half plane. Image meaning, what does this function do to a half plane? Okay. So in general, a half plane is defined by some inequality involving the real part of z and or the imaginary part of z. The half plane we're going to look at for this example is going to be the region S, which is going to be the collection of complex numbers where the real part of z is at least 2. So if we were to graph that region S, what would we get? Well, let's mark 1, 2. We are allowed to have real part equal to 2. It's a weak inequality. And we want every point where the real part is bigger than or equal to 2. So that's every point to the right, well, on the line and to the right of the line. And what do we know? Well, in the language of the of chapter 1, this is a closed set because it has all the points on its boundary. It's connected. There's just one piece. It's not bounded because you can run off to infinity. It's not open, and it's not a domain. Okay, so just quickly running through those. We want to think about this as like the z plane. This is our domain over here. And then on the right, what we're going to do is we're going to graph the w plane. That is, what happens to things in the z plane when we apply the function f to them. This is the codomain plane. And f is going to take us from the left picture to the right picture. I don't really have a good color for that, but f takes us from the left picture to the right picture. Now, multiplication by I has principal argument pi over 2, and multiplication by I is therefore rotation by pi over 2, right? Because when you multiply complex numbers, you add their angles and you multiply their modulus. The modulus of I is 1, so you're not going to multiply any modulus, but you will add an angle of pi over 2 to the existing argument. So for example, this point here at 2 is going to go up to 2i. It's going to go up to there. And what we're going to do is we're just going to rotate that whole line along the circle of radius 2 until we get to there. And the output region is this sort of purple region here, or the image of f of s under f, which we'll typically write f of capital S, meaning where does f send all of s? So in this case, multiplication by I sends the half plane, real part of z bigger than or equal to 2, to another half plane, and that's the half plane imaginary part of z is bigger than or equal to 2. So we can write that out explicitly. So it's the z's in C such that the imaginary part of z is at least 2. And furthermore, we can be even a little bit more algebraic about this if we want. So So this is the answer. We're done. Let's highlight it in yellow to indicate we're done. But we can arrive at this answer in a different way using just the description of F and S without having any picture. So let's do that. So let's do it, I'll say algebraically. So S is the set of x plus I y's such that x is at least 2. Right? So the real part is at least 2. F of S is the set of all f of x plus I y's such that x is at least 2. We just apply f to that set. And the f function is the multiply by I function. So we multiply that by I such that x is at least 2. And we multiply by I, the I squared on the y is going to give us a negative y such that x is at least 2. And it really doesn't matter what y is. Y ranges over all real numbers. So negative y will range over the same amount as y. So this is really just a collection of all z's and c such that the imaginary part, because x is now the imaginary part of that expression, is at least 2. And that's what we found. So we got the image of S algebraically is still the same set. And again, it is also another half plane.